This is the last talk of the day, and it's my first 1 a.m. talk. So yeah, thank you very much for giving this talk. So yeah, Maas is from IST Austria. So the floor is yours, Jan.
Okay, thank you very much. Yeah, thanks a lot for the kind invitation. It's really a pleasure to speak at this very nice and interesting program. Okay, so I will continue kind of the story of today, which is about optimal transport. And my talk will, of course, build on some of the previous talks by Michaela and also by Marco. And what I will focus on mainly in this talk is sort of the additional difficulties and challenges which arise if you try to apply some ideas from optimal transport in the setting of discrete systems, and also a little bit about what happens if you try to apply these ideas in quantum settings. Okay, but kind of the starting point of my story will overlap a bit with what we've seen before. This is kind of this circle of ideas about connecting optimal transport to, on the one hand, sort of PDEs, in particular diffusion equations, and in another direction also to geometry, and in particular to Ricci curvature. And I think that's something that we didn't see so much yet during this workshop, so that's also something I would like to talk about. Okay, so to keep the talk a little bit self-contained, here's once again the optimal transport problem, which we by now saw many times this week. So you're given two probability measures, and you want to transport mass from one configuration to the other. So a natural setup, I mean, if you want to do this in great generality, is to work in a metric space. So I take two probability measures, mu and nu, on a metric space X. And then the important concept is that of a transport plan or a coupling between those two measures, which is just a probability measure with marginals mu and nu. So if I project onto the first coordinate, I get mu, and if I project onto the second coordinate, I get nu. And then the optimal transport problem, the Maas-Kantor-Robic problem that we saw many times, is the following. You would like to minimize the total transport cost. So the integral of the cost function C, you want to minimize with respect to overall coupling, so overall transport plans connecting these two probability measures. Okay, and then, well, what we already saw in Michaela's lecture is that there is a very beautiful connection to PDEs, to diffusion equations, which goes back to the work of Jordan, Kinderlehrer, Otto at the end of the 1990s. And this involves a very particular optimal transport problem, namely the one where the cost function is the square of the distance, which corresponds to the so-called Wasserstein or Kantor-Robic metric on probability measures. So this is the optimal transport problem with the quadratic cost function. Then the second main actor in the story is the entropy, or the negative of the Boltzmann-Shannon entropy. So for probability measure mu with density rho with respect to the Lebesgue measure, the entropy is the integral of rho log rho dx. Well, and the third object is the diffusion equation or the heat equation, which you can regard as an evolution equation in the space of probability measures. And then the beautiful result connecting those three is this theorem by Jordan, Kinderlehrer, and Otto, which says that the heat flow is the gradient flow of the entropy with respect to this Wasserstein metric from optimal transport. Yeah, so intuitively speaking, it's the steepest descent. So the diffusion equation is exactly the evolution equation, which tries to decrease the entropy in such a way that you don't move too much with respect to the Wasserstein metric. Okay, we already saw this before, and we'll also see it tomorrow. But let me give you one way to look at this result, so you can actually interpret it at various different levels. But I will tell you one way how to do it. So here's once again the statement of the theorem. The heat flow is the gradient flow of the entropy with respect to the Wasserstein metric. And well, if you want to make this kind of rigorous, then of course the question that arises is actually how do you make sense of gradient flows in a metric space? Right? Because a priori, the Wasserstein metric on probability measures defines a metric, but you don't really have at least not immediately, you don't have a Riemannian structure. So it's not a priori obvious how you make sense of such a concept. And well, there are different ways to do it, but one of them I can explain in 3 lines on this slide. And to see what's going on, it's instructive to look at the simplest possible setting, and namely at gradient flows in Rn. So if I'm in Euclidean space, Rn, and if I have a smooth and convex functional, then there's actually a very, very nice description of gradient flows. Namely, if I have a curve U in space Rn, then the following are equivalent. So the first condition is that U solves the gradient flow equation. So it means that it solves this ordinary differential equation U prime equals minus gradient of phi of U. So that's the usual differential equation, which means that this curve is the gradient flow for the functional phi. But you can do something nice, namely because the functional phi is convex, you can actually rewrite this differential equation as a system of inequalities. Just by using the variational formulation for the gradient of a convex function. So it's sort of the just the tangent line description of the gradient of a convex function. You see that this gradient flow equation is actually equivalent to this system of inequalities, since the function was convex. But now what you can do is, if you look at the left-hand side of this expression, is you can actually rewrite this. Namely, you can write this as the derivative of the squared distance between ut and y. Just by applying chain rule, you see that these are the same objects. And now there's something interesting, namely if you look at this second inequality, you actually see that it makes sense in great generality, because there's no gradient of phi appearing anymore. And also the derivative of u that we saw in part 1 is not present in part 2, right? Because we have here the derivative of a scalar quantity, namely the square of the distance. So the second formulation is completely equivalent to the first one, but it has the great advantage that it makes sense actually in metric spaces. Because the only thing which you need to have in order to formulate this, this system of inequalities is you need to have a distance for the left-hand side, and you need to have the functional. So this system of inequalities actually characterizes gradient flows, at least in the presence of some convexity. And you can actually take this as a definition of gradient flow in the metric space. And now one way, sort of going back to this theorem by Jordan, Kindler, Otto. So one way to make rigorous sense of this theorem is actually by transferring this formulation also to the Wasserstein space. So you have a solution or a curve of measure satisfies the heat equation, if and only if it satisfies the same evolution variational inequality as we saw below, but now with the Euclidean distance replaced by this Wasserstein 2 metric, and the role of phi is now taken over by the entropy. So this is a metric formulation of the gradient flow structure for the entropy in the Wasserstein space. Okay, well, this result doesn't stand on its own. I mean, there are actually many extensions of this theorem. It's been very influential. So this applies to extremely general spaces. It's been extended to Riemannian manifolds, to infinite dimensional spaces like Hilbert spaces, Wiener spaces, to sub-Riemannian spaces like Heisenberg group, Alexandrov spaces, so very non-smooth objects. And sort of this line of research kind of culminated in the work by Ambrogio Chili-Savary, who actually made sense of this gradient flow formulation in the setting of metric measure spaces. And so in full generality, they showed that sort of the heat flow, which you can define as the gradient flow for the Dirichlet energy in L2, coincides with the gradient flow of the entropy in the Wasserstein space. Okay. Well, you might ask the question, actually, why would you do this? Because, of course, the diffusion equation is one of the simplest PDEs. It's a linear equation, so why would you write it as a complicated evolution equation in this nonlinear fashion? Well, there are actually good reasons for that. So one of them is that it does not only apply to the diffusion equation, but it actually works for a very large class of dissipative equations, like Fokker-Planck, porous medium, McKean-Vlasov equations. It's physically appealing. It also connects to probability, to large deviations. It comes with good time discrete approximation schemes. I think a gradient flow structure gives you a kind of a natural way to write the time discretization. And also it applies to non-smooth problems. As you saw before, it applies to very general situations. It gives you interesting inequalities and estimates. So functional inequalities, connecting various quantities like entropy, Fisher information, Wasserstein metric. And it also gives information about speed of convergence to equilibrium, for instance, for porous medium equations. And finally, another advantage is that this formulation is actually closely connected to geometry, and in particular to Ricci curvature. So now I would like to say a little bit more about this geometry connection. Okay, so well, before making this more formal, let's look first at this cartoon, which is supposed to describe this thought experiment, which Cédric Villani in his book called the lazy gas experiment. And the idea here is that you would like to, so suppose that you're on a manifold, like on this sphere drawn below, and you would like to understand whether you're on a positively curved space or on a negatively curved space or on a flat space. Right? But you don't want to compute like curvature tensors and things like this. So you want to have a more robust approach. And the way to do it is by the following experiment. So you take a gas living on this manifold, so a cloud of particles, and at time 0, you force your particles to be located in this little green area at the left. I don't know if you see my cursor moving.
Yes.
Okay, very good. Okay, so that's the cloud of particles at time 0, located over here. And then at time 1, you ask your particles to be located into this green area over here. But your particles are lazy, so they want to spend as little energy as they can. So they're going to travel along shortest paths. And of course, on manifold, the shortest path is not a straight line, but it's a geodesic. And now you see, I mean, you see drawn in this picture what happens in the presence of positive curvature. So if you're on the sphere, what happens is that initially your geodesics tend to spread out, so they diverge, and then at the end they converge again. And so if you look at where your cloud of particle is at the midpoint, you see actually that they're in this red area over here, and they're actually much more diffuse than at the boundary points. So the mass is much more spread out. Okay, what you do is you keep track of the entropy along this interpolation. So if I talk about entropy, I mean actually relative entropy with respect to the volume measure, so the integral of rho log rho. So not minus rho log rho like physicists would put it. But if you keep track of the entropy, well, what does the entropy measure? It measures how spread out my mass is. So in particular, at the midpoint, my mass is much more spread out. It means that the entropy, or the relative entropy with respect to the volume measure, will be lower. So if I draw the graph of the entropy, you see that you get this convex profile. So what you learn from this experiment is that the positive curvature of the sphere is actually strongly connected to this convexity of the entropy along this interpolation. Okay, so and you can turn this idea into mathematics. And there's a long story behind this, but this really started with the work by Robert McCann in '94. So what he showed is that if you do this not on a manifold but just on flat space, just in Rn, then what he proved is that the entropy is actually convex along geodesics in the Wasserstein space of probability measures. Yeah, so the entropy is a convex function of along linear interpolation, just because rho log rho is convex in rho. But it's also convex along this Wasserstein interpolation, which is a very different thing. Okay, and then after this result got extended to Riemannian manifolds in a series of works. And there the statement is that for a Riemannian manifold M, the following assertions are equivalent. Namely, firstly, that the Ricci curvature of your manifold is bounded from below by kappa, where kappa is just a scalar constant. So if you don't know what Ricci curvature is, it doesn't matter for this presentation very much, but it's one important concept of curvature. And this condition is equivalent to this to the convexity of the entropy, or more precisely, the kappa convexity of the entropy along geodesics in the Wasserstein space on your manifold. So this kappa convexity means that you have the convexity of the entropy minus some correction involving your constant kappa coming from the curvature and the Wasserstein metric. Okay, so this is a beautiful characterization of this lower bound on the Ricci curvature. And just like we have in this gradient flow characterization, the interesting thing here is that the second part is much more robust than the first part. Right? Because to be able to talk about Ricci curvature, you need to define the Ricci tensor, for which you need to have a smooth Riemannian structure. Yeah, but to make sense of this second condition, you actually need much less structure, right? Because you need to be able to talk about the entropy, for which you need to have a reference measure. And you need to be able to talk about Wasserstein metric, and for which you need to have a distance. And so this actually makes sense in metric spaces endowed with a measure. So this was the starting point of a theory of lower Ricci curvature bounds in metric measure spaces, initiated by Lotz, Sturm, and Villani. So you don't directly make sense of a Ricci tensor, but you can actually make sense of a lower bound on the Ricci curvature without really defining the Ricci curvature itself. Yeah, and that's, I mean, already having this lower bound is kind of a crucial thing in many applications. Okay, so here's that, this is written as a definition. Well, this is what I just said. So a metric measure space, XDM, satisfies this lower bound on the Ricci curvature if this convexity inequality for the entropy holds along all geodesics in the Wasserstein space of probability measures.
So where does M show
up? Yeah, so M shows up in the entropy. So it's the entropy, actually the relative entropy with respect to the reference measure M.
Okay.
Yeah, thanks for the question. Yeah, so the M shows up in the entropy and the D shows up in the Wasserstein metric. Okay, so this is the starting point for a rich theory. It's the important points are that this applies to a wide class of metric measure spaces without necessarily having a smooth structure. It gives you many interesting consequences. So here are a bunch of inequalities noted. So Sobolev, Talleyrand, and Poincaré inequalities. It's also connected to concentration of measure inequalities and many other things. And also it's stable. Yeah, so it's stable under passing to the limit of of your metric measure spaces. So it's stable under the notion of measured Gromov-Hausdorff convergence. So there's now a rich theory of optimal transport in this very general setting, and this has become a very active research area. Okay, so this is extremely general, but let's now move back and ask, well, what happens if we try to apply these ideas to the setting of discrete spaces? Okay, and to get a feeling for what's going on, let's do something extremely basic. Let's look at the simplest space we can imagine, which is the 2-point space. So just 2 points, 0 and 1. Well, of course, in the 2-point space, we can write every measure or every probability measure as a convex combination of two Dirac masses. So mu alpha is the measure with mass 1 minus alpha at 0 and mass alpha at 1. Okay, let's now see what actually this Wasserstein metric looks like in this context. Well, if I compute this Wasserstein 2 metric between mu alpha and mu beta, well, what you get is the following. You get the square root of the absolute value of alpha minus beta, because you get the distance square, which is equal to 1, times the amount of mass that you're transporting, which is alpha minus beta. And at the end of this definition of Wasserstein, you take the square root, because it's Wasserstein 2. Okay, so this is the Wasserstein metric on this 2-point space. And let's now see what we can say about geodesics. So suppose that I have a geodesic in the space of probability measures, which I can write as mu of alpha t. Well, what does it mean to be a constant speed geodesic? It means that the distance between the measure at time t and the measure at time s is proportional to t minus s, right? But by what we just saw is that this Wasserstein metric is also equal to the square root of alpha t minus alpha s. Yeah, and if you now stare at this identity and compare the left to the right-hand side, then you see that it means that actually alpha must be Hölder continuous with Hölder exponent 2. But of course, this cannot be unless the curve is actually constant. So what this simple computation show is actually that there do not exist any non-trivial geodesics in the Wasserstein space over this 2-point space. Every geodesic is constant. And that's not a coincidence, because you can actually show that the Wasserstein space of probability measures, with respect to this Wasserstein 2 metric, is a geodesic space, if and only if the underlying space is geodesic. So it means the geodesic space is a curve in which is a space in which you can connect every pair of points by a constant speed geodesic. So what this basically tells you is that if you start with a discrete space and you look at the Wasserstein space, so the Wasserstein 2 space over this discrete space, you will not find any geodesics. And that's bad news, because it means that what I told you before actually does not apply. Namely, you will not find any curve of finite length. So you don't find any geodesics. So you cannot talk about geodesic convexity of the entropy. And you can also not find any curve of finite length. So you cannot find any gradient flow in the space of probability measures, and that with this Wasserstein 2 metric. So this story before is extremely general. It applies to very general metric spaces, but it breaks down if you try to apply it directly in a discrete setting. Okay, so let's see what we can do nevertheless, because it turns out that there's a way to get around these difficulties. So let me start with writing down the discrete setting that we look at. So the starting point is that you take a discrete set. So let's just take a finite set of points x, and then you can. It's natural to take as a starting point L to be the generator of a Markov chain, which you can write in this form. So L of psi is like a discrete Laplacian, like written over here, where Qxy is the transition rates between x and y. Or equivalently, you can start with a graph or a weighted graph. Okay, so by sort of standard Markov chain theory, if I take an irreducible Markov chain, or in other words, if the associated graph is connected, there exists a unique invariant probability distribution. Let's call this pi. And of course, there's a natural entropy in this context, which is just the relative entropy of a measure mu with respect to pi. Right? Just the same as we saw before, but now there's no integral, but there's just a sum. And now the question that's kind of is natural in view of this gradient flow description of the diffusion equation is the Kolmogorov forward equation, if you want, the discrete heat equation associated to this Markov chain, So the flow of probability measures, which describes the evolution of the law of your Markov chain. Is this a gradient flow of the relative entropy with respect to some metric on the space of probability measures? So this would be the direct analog of this JKO theorem. Okay, and what we saw in the previous slide is that this is not going to work if you take maybe the first attempt, maybe if you take Wasserstein 2, because I argued that there do not exist any gradient flows in this Wasserstein space of exponent 2. Nevertheless, you can try to solve this problem on the 2-point space, and if you do it on 2-point space, here's the answer. So you can indeed find the metric on probability measures, and it's given by this strange formula involving some hyperbolic arctangent. So probably not the first metric you would try if I would ask you to guess. Okay, so the question is, of course, where does this come from, and can we make sense of this also in a little bit more interesting discrete settings, namely on arbitrary discrete spaces? So this can be done, and to do that, it's again instructive to look at the continuous setting. So let's go back to Rn, and let's look at this dynamical characterization of W2 that also Michaela already presented. Where you change a little bit the point of view, instead of looking for optimal couplings between two probability measures, you're trying to find a curve in the space of probability measures. So a continuous time interpolation connecting two given densities. So if you start with ρ0 and ρ1, you're connecting them in continuous time by a curve of measures. Okay, and then what you want to do is you want to regard again your measure as a cloud of particles, and you want to track sort of the trajectory of each of your particles. And there is a velocity vector field which describes the movement of these individual particles, and the velocity vector field I denote by psi, depending on t. Okay, and here's this the Benamou-Brenier formula that we saw this morning. Well, this gives a dynamical formulation of the Wasserstein metric in terms of this continuous time optimization problem. And it tells you that you can actually compute the Wasserstein distance by minimizing the total kinetic energy. So the square of this is the square of the velocity vector field integrated against the mass. So this is really a kinetic energy integrated in time. And you minimize among all curves of probability measures connecting your given boundary measures. So this is the formula due to Benamou and Brenier from 2000. Okay, so this is an important theorem in continuous optimal transport. Maybe as a just one comment, you can actually assume without loss of generality that your vector field is a gradient, because the optimizers will always be gradient vector fields, modulo some technicalities that I would like to sweep under the rug now. So we can always assume that the optimal vector field is actually a gradient in this Benamou-Brenier formulation. Okay, so this is a theorem in the continuous setting, namely the equivalence between equivalence between static and dynamical optimal transport. Yeah, so this metric defined in terms of the Monge-Counter-Rollins problem is equivalent to this dynamical optimization problem. So in the discrete setting, this is no longer true. Yeah, so there's no longer equivalence between this dynamical and statical picture of optimal transport. But it's sort of tempting now to try to do something similar in the discrete setting. So in the discrete setting, you can also look at sort of dynamical optimal transport problems. So here's once again the continuous formulation, and here's now a sort of an attempt to define an analog in the discrete setting. So we're in the setting of the X, and I would like to define this dynamical optimal transport problem. Well, and if you try to do it, well, you can just try to replace all the continuous objects with their discrete counterparts, right? So the time integral stays the same. The integral in space is replaced by a sum. The gradient here in the continuous setting you don't have on the graph, right? But the next best thing is sort of this discrete derivative. Then here there's this Lebesgue measure, which will be replaced by sort of some data of your graph. So this is this omega xy, which contains the transition rates of your Markov generator in the invariant distribution. But then there's something left open here, and in the continuous setting you have the density at time t. And so also here in the discrete setting you would like to write the probability density. But now you see that there is some issue, because in the continuous setting you're actually looking at the velocity vector field at a point x, and you multiply it by the density at the same point x. But if you try to do it on a graph, then you see that this velocity or this gradient is actually not defined at a single point, but it's defined between 2 points, right? It's defined on an edge of your graph, whereas your mass lives at the vertices. And so there's some ambiguity here. So should you put here rho t of x? Should you put here rho t of y? Or should you put something different? Yeah, so the problem is, in some sense, the mass is defined on vertices, but your gradient is defined on the edges of your graph. Okay, and well, what turns out to be a natural thing, and I will explain on the next slide why, is that you put some function actually depending on the density at x and the density at y. So this is your measure divided by the reference measure. So the density at x, density of y, and you take some average of these densities. And of course, you have some freedom to choose your favorite average. So you can take just the arithmetic mean or the geometric mean, for instance. But what turns out to be very natural is to take the logarithmic mean of these densities, which is defined by this expression. So the logarithmic mean of A and B is defined by this nonlinear average. Okay, so this defines a sort of an analog of this Benamou-Brenier. And for the continuity equation, you can do something similar, right? So you replace all the continuous objects by their discrete counterparts. So the divergence is replaced by a discrete divergence. But then you run into the same issue that you want to multiply a density in a vector field. And you resolve this again by putting here this logarithmic mean of your densities. Okay, so this is a direct analog of Benamou-Brenier.
Question.
Yeah.
The logarithmic mean of two densities is a density.
Yeah. So what you do it pointwise. So you at each vertex of your graph, you take the logarithmic mean of the density at that vertex. But the logarithmic mean is not defined at a vertex, right? It's between two vertices. So it's in some sense it's an object which lives on the edges.
I see.
Right, and it's not normalized or so. Yeah, thanks. Okay, so you see that there's a natural analog of Benamou-Brenier, but you have some additional freedom in the discrete world because you can play around with this mean. Okay, so what can we say about this metric? Well, the good news is that it actually much better behaves than this W2 distance, because this is actually a distance which is induced by a Riemannian metric on the space of probability measures. So this is a Riemannian distance. And the theorem, which sort of maybe justifies why we actually are interested in this rather complicated distance, is that it allows you to have a discrete version of this JKO theorem. Yeah, so you can show that the discrete heat flow, or in other words, this discrete Fokker-Planck equation or discrete Kolmogorov equation, in any case, the flow of probability measures given by the Markov chain is the gradient flow of the entropy with respect to this distance on the space of probability measures. Okay, and this result was actually discovered in kind of different communities in slightly different versions around the same time. So independently also by Alexander Mielke in the context of reaction diffusion equations, and by Chao, Wang, Li, and Zhu in the context of numerics for Fokker-Planck equation. Okay, well, I hope this sounds kind of natural, but of course the question is, why does this logarithmic mean show up? Because that's not at all canonical. Well, here's some short explanation. So let's look again at the continuous setting. So in the continuous setting, if you want to write the heat equation as a gradient flow, what you want to do is you want to write it as a continuity equation, just as we saw in Michaela's talk. So you want to write this heat equation into this form. So dt rho plus divergence rho psi equals 0. Well, this you can do, and this you can actually easily check. So if you plug in psi equals minus the gradient of log rho, then you see that you get exactly the heat equation, right? Because rho times the gradient of log rho gives you the gradient of rho, and then the divergence of the gradient is Laplacian. Okay, so that's kind of a trivial computation in the continuous setting, but if you discretize it, it actually breaks down, because what you're using here is actually the chain rule, yeah, to relate the gradient of rho to the gradient of log of rho. Yeah, so that's the chain rule, but this chain rule will fail in a discrete setting because discrete derivatives don't satisfy a chain rule. Okay, so and to get around this difficulty, that's exactly why you use the logarithmic mean, because this logarithmic mean between rho x and rho y, I wrote it down on the previous slide as this sort of in this integral formulation. You can actually, if you do the computation, you can actually see that you can also write it as this difference quotient. So it's rho x minus rho of y divided by log of rho x minus log of rho of y. So you can actually imagine, hopefully, that you can use it in computations to sort of compensate for the lack of a discrete chain rule, at least for this particular log function. And that's exactly what you need if you want to prove this gradient flow structure. Okay, so that's the discrete dynamical transport metric, which gives us now a very nice discrete version of this result by Jordan, Kindler, Otto. Okay, and then it's well, in view of this geometry which I talked about before, it's also natural then to try to use this idea also to talk about Ricci curvature for discrete spaces. So Ricci curvature for graphs or Ricci curvature for Markov chains. So you can now define, given a Markov chain with transition rates q and invariant measure pi, you can say that it has a Ricci curvature bounded from below by kappa if the relative entropy is kappa convex along geodesics in this with respect to this optimal transport metric. And these geodesics do exist because this is really a Riemannian metric. Okay, so here's just a list of examples to show you that you can actually compute this in a bunch of cases. So it, in particular for the discrete hypercube, so it behaves well with respect to the dimension. It has sort of the natural tensorization property, and also for some simple models of interacting particle systems, you can actually compute this Ricci curvature. But let me also mention that. Well, this is kind of also an active field of research, trying to understand curvature of discrete objects. And this is by no means the only way to define a notion of Ricci curvature in the discrete world. Well, it's actually not equivalent to several other definitions. So another popular way to understand Ricci curvature for graphs is, for instance, introduced by Jan Olivier. And this is based on also an optimal transport. But it's based on contractivity of sort of discrete heat semigroups with respect to a Wasserstein-Wam metric. And, well, I explained before that this Wasserstein-2 is not well behaved if you apply it in discrete spaces, but this Wasserstein-Wam metric is actually much better behaved. And so you can use it. Sorry?
It's just sound coming from outside. Sorry.
Ah, okay. I thought someone else had some question. Okay. So this Wasserstein-1 metric you can actually also use to define a notion of curvature. But then this Wasserstein-1 doesn't work if you want to have a gradient flow structure. So for the gradient flow, you have to work with some kind of analog of W2 as we used. Yeah, and there are also the other notions of curvature are sort of based on Bakry-Emery curvature, which is sort of a calculus based on discrete gradients and discrete Laplacians, which has also been very powerful in continuous settings and which has also been sort of intensively studied in the discrete world. Okay, but one particular nice thing about this this notion of Ricci curvature based on entropy and optimal transport is actually that it allows you to prove kind of Sobolev type inequalities, in particular this kind of discrete Bakry-Emery type theorem. So the formulation is that if you have a reversible Markov chain and kappa is strictly positive, then if the Ricci curvature is bounded from below by the strictly positive constant, then you actually have a logarithmic Sobolev inequality. So this is this inequality relating the relative entropy with respect to the stationary distribution to some other object, which is well, it's some analog of a Fisher information, so some functional arising in information theory. And the constant in this inequality is given by the curvature of your Markov chain. And the interest in this kind of functional inequalities is that they actually imply quantitative bounds on the rate of convergence to equilibrium for your Markov chains. So this implies exponential decay of the relative entropy measured in this entropy. Yes, exponential decay of the relative entropy with convergence rate kappa. So this Ricci curvature can be used to say something useful about speed of convergence to equilibrium. Okay. Yeah. So let me also mention that sort of this discrete gradient flow structure actually has sort of also sparked some many sort of follow-up works. And there are sort of various interesting gradient flow structures in slightly different settings. So in particular, it also applies, I mean, you don't really need to have discrete spaces, but it applies also to jump processes on more general settings, like Levy processes, for instance. It not only applies to kind of linear equations like this Markov chains, but also to non-local interaction equations on graphs, and also to some nonlinear PDEs like discrete porous medium equations. It also extends very naturally to chemical reaction networks, and so to chemical master equations and the associated Liouville equation. And it's also closely related to some optimal transport metrics which arise in the setting of dissipative quantum mechanics, which has also been studied by many people in recent years. And the idea is there that you try to do optimal transport, but not between probability densities, but optimal transport between density matrices. So positive definite matrices with trace 1. Okay, and I would like to say a few words also on this non-commutative version of optimal transport. And so optimal transport for density matrices. Yeah, and kind of the natural question there is again, is there some version of the JKO theorem, so this gradient flow structure, in the setting of dissipative quantum systems, like for instance are studied in quantum information theory. So let me give you sort of a one-slide introduction to set the stage. So we're interested in the dynamics of open quantum systems, which are sort of, well, mathematically they're sort of non-commutative analogs of these Markov chains, but they describe kind of physical systems coupled to some heat path. So the setup is that you take a Hilbert space, as usually in quantum mechanics, and let's assume that everything is finite dimensional. It will simplify things a lot. but it's already very, very non-trivial, and many essential ideas are present in this setting already. So let's just take a finite dimensional Hilbert space. If you want, just take the n by n matrices. Then, so if the natural counterparts to the probability densities are these density matrices, as I mentioned before. So, so this is the set of density matrices, all positive definite matrices rho with trace 1. So if you can view this as a strict extension of what we saw, what we did before in the discrete setting. If you think about a discrete probability density as some diagonal matrix with positive entries summing to 1, then you see that you hear of something similar, but you actually allow sort of matrices which are not necessarily diagonal. So you get objects which don't necessarily commute with each other. Okay, so then it's also natural to look at well, the analogs of Markov semigroups in this context. So these are semigroups now acting on matrices. Well, they are supposed to have the following two properties. Well, first of all, they should be trace preserving. So the trace of PT of rho should be equal to the trace of rho. And secondly, they should also preserve the positivity of matrices. And so if you take a positive definite matrix and you have your semigroup acting on it, then you should again get a positive definite matrix. This complete positivity refers to the fact that you want this property also to be true if you actually tensorize with an identity matrix. So that's a technical assumption, which is important. Okay, so this is a well-studied class of systems in quantum mechanics, quantum information theory. In particular, there's a characterization of what these generators for such objects look like. So the generator of such a Markov semigroup or a quantum Markov semigroup, it's given by this Lindblad formula. So you can write the generator in the following form. It consists of two parts. So the first part is a commutator with some matrix H. That's this guy. And then there is like a second order part, if you want, which is a sum of different terms. And they also involve commutators of rho and a bunch of fixed matrices Vj. And so the precise form is maybe not very crucial for the understanding of this talk, but in any case, there is a good understanding of what these generators look like. And they're in many ways sort of analogous to generators of Markov chains. Okay, so there's also a good concept of entropy. So suppose that you have a stationary state for such an evolution equation. So it means that L of sigma equals 0. Then you can actually consider the quantum relative entropy. So entropy rho with respect to sigma. It's given by the trace of rho log rho minus rho log sigma. So this is to be understood in the sense of spectral theory. So rho log rho is a matrix, and you take the trace of this matrix.
Yeah.
Okay, so this is the natural. Yeah.
Can I ask a question? So I know very little in quantum. Like, to just set concrete things, is there some notion of like ground motion over this matrices, or maybe it's the equivalent of Ornstein-Uhlenbeck process? Like, when I think about a semigroup, just to have like a concrete example of what a diffusion Markov diffusion process would be. Do you have any concrete example of this?
Yeah.
Okay.
Yes, actually, Ornstein-Uhlenbeck will come in, I think, in 2 or 3 slides.
Okay, thank you.
And there's also a concept of Brownian motion related to these objects. So these kind of objects are well studied. I will come back to Ornstein-Uhlenbeck in a few slides. Okay, so there's a natural notion of entropy, and well, it goes back also to the 70s or so that this entropy is actually monotone along the flow. And so the relative entropy also in this quantum setting is actually decreasing along the evolution of your quantum Markov semigroup. Okay, so then it's natural to ask the thus the question actually, well, it's written here. Can we now formulate this sort of non-commutative analog of this Markov chain evolution, this Limblad equation? Can we write it as a gradient flow of the relative entropy? Yeah, it's written here. Okay, so to understand this question, let's make some simplifying assumption. Namely, let's assume first that our generator is actually self-adjoint. Yeah, so it's self-adjoint with respect to this natural scalar product on matrices given by this trace of A star and B. And that's a symmetry assumption which actually simplifies things quite a bit. Okay, then it's actually known that you can actually write your generator as a Laplacian in the following sense. Namely, you can write your generator as a sum over J of these, well, kind of derivatives, but they're not really derivatives, they're actually commutators. So dj of A is the commutator of A with respect to these operators Vj that we saw before. So the Vj's are fixed matrices. And this dj dagger is actually the adjoint of dj with respect to this trace duality. But the point is that you can really write your generator as a Laplacian, where you replace derivatives by commutators. Okay, and once you know this, it's again very natural to play the same game as we did in the discrete setup. Namely, it's natural to define an optimal transport distance, a dynamical optimal transport distance on density matrices by writing this Benemou-Breuer type formula. Right? So again, I sort of well, wrote something very similar to what I wrote in the discrete setup, with the difference that sort of derivatives or discrete derivatives are now replaced by these operators dj, which are commutators. And I do the same thing here in this kind of kinetic energy term. The integral is replaced by the trace, as usual in the non-commutative setting. And for the continuity equation, you do something similar. Okay, but again, we see that there is an issue here. Namely, just as in the discrete setup, where we couldn't really multiply things which live on edges with things which live on vertices, there's also some problem here if we try to multiply things, right? Because these objects are matrices, so multiplication does not is non-commutative. So it actually matters whether we multiply, well, for instance, rho with this operator from the left or from the right, or whether we do something different. So the question is basically, how do you actually make sense of this product? So I didn't specify what this fat dot actually means, but that's the question. So what's the right way to define this multiplication in this non-commutative setup? And again, what we actually need is we need some version of this chain rule, which was also a key ingredient to make sense of the discrete gradient flow structure. So the question is now: is there now a non-commutative chain rule, basically for these commutators? Okay, and the good news is, well, there is actually one, and this can also be shown on one slide. So let's try to figure out what is the right way to multiply here. Recall that these operators dj are actually commutators with these matrices vj. Now commutators, they satisfy Leibniz rule. So we have this identity, dj of AB is dja times B plus A times djb. This you can, of course, iterate. So if you apply this n times, you find that the dj of A to the power n can be written in this form. Okay. Now what you can do is you can apply this identity to the matrix rho to the power 1 over n. And so if I plug in rho to the power 1 over n here, I get dj of rho on the left-hand side And on the right hand side, I replace a by rho to the 1 over n 3 times. So you find this interesting identity relating the derivative of rho to the derivative, or actually this kind of commutator of this rho to the 1 over n. Okay, and now this identity holds for every n, so it's very tempting to pass to the limit. And then you recognize actually that the right-hand side you can view as a Riemann sum. So if you let n tend to infinity, what you find is that dj rho can be written as an integral from 0 to 1 of rho to the s times dj of log rho times rho to the 1 minus s ds. So if everything would commute, it would be just sort of saying that dj of rho is equal to rho times dj of log rho. But now we found a particular sort of non-commutative multiplication, which gave us this chain rule. Yeah, and you see that it's very reminiscent of what we had in the discrete setup, where actually this logarithmic mean appears. So this is actually some kind of non-commutative version of this logarithmic mean. Okay, so this suggests now the right way to multiply, and now here we can write a theorem. So suppose that I have this Lindblad operator, so this generator of a quantum Markov semigroup with given operators Bj, then I can define an associated transport metric. So here I dropped again the same Bonnemou-Brenier type formula as I did before. So you minimize some kind of analog of a kinetic energy over all solutions to the continuity equation connecting to given densities or to given density matrices. So this is the exact analog of Bonnemou-Brenier, but you replace your derivatives by commutators, and we use this multiplication given by this fat dot, which is given by this non-commutative logarithmic mean. Okay, and then the theorem is that if you do that, so remember we made this assumption of self-adjointness with respect to trace duality, then this Lindblad equation is actually the gradient flow of the von Neumann entropy with respect to this optimal transport metric. So in this sense, what this theorem tells you in some sense is that this metric is actually a natural replacement of this Wasserstein metric, but now acting on in a non-commutative setting, so as a metric between density matrices. Okay. Yeah, so I mentioned that we made sort of this simplified assumption of symmetry. So let me show you one slide. I'm not going through the details, but you can pause the video on YouTube if you want. So if you don't make this assumption, but if you assume that actually your generator is still self-adjoint, but with respect to some non-trivial invariant state, then you can still obtain a gradient flow structure, which is sort of similar in spirit, but the algebra gets a little bit more complicated, but it extends to this case as well. So we have a gradient structure for sort of arbitrary dissipative quantum systems, at least in finite dimension, under this detailed balance condition or this self-adjointness condition with respect to this scalar product. Okay, and yeah, to come back to this question that was asked. So an example, or sort of one of the simplest examples is a quantum version of the Ornstein-Uhlenbeck semigroup. And so in the classical setup, the Ornstein-Uhlenbeck semigroup is kind of the diffusion semigroup for which the stationary distribution is the Gaussian measure. There's something similar in the quantum setup, but everything is defined in terms of operators, of course. So the starting point is that you take an operator satisfying this kind of commutation relations, which are called canonical commutation relations. You can actually realize them concretely on some L2 space and out of the Gaussian measure. So the particular form is not very important, but I wanted to write it down. And then there's a natural analog of quantum of Ornstein-Uhlenbeck given by this formula. And it's exactly of this Lindblad form that I showed you before, where actually these operators A and A star appear. So these are the annihilation and the creation operator for a boson quantum system. So this is a kind of a canonical operator arising in quantum information theory. It has a Gaussian stationary state. And so in this sense, it's also an analog of Ornstein-Uhlenbeck. And one of the things that we showed using these optimal transport ideas is some analog of this logarithmic Sobolev inequality that I already showed in the discrete setup. Or in other words, some exponential decay of this quantum relative entropy along the semigroup generated by this quantum Ornstein-Uhlenbeck operator. And this is some analog of the logarithmic Sobolev inequality in this quantum setup. Okay, well, if you try to obtain such a result sort of by direct methods, then it's actually not so easy in this non-commutative setup, because computations get very quickly kind of out of hand. But this optimal transport point of view is very fruitful, because it gives you kind of some structure behind these computations, and we actually gave kind of a relatively soft proof of this result, and kind of the things which go into the proof is well, very algebraic things. So for instance, some commutation property between the semigroup and these partial derivatives, so these commutators. So this is just an identity that you can check. And the other thing which goes into these kind of proofs is some convexity inequality for matrices, which is given by this formula, which looks maybe a bit complicated. But so R and A are matrices. So R is positive definite and A is arbitrary. So if those were scalars, then the right-hand side would be A squared divided by R. And A squared divided by R is actually a convex function, jointly convex in A and R. And also in this non-commutative setting, this kind of object is A squared divided by R is actually a convex function, even if these objects are matrices which don't commute with each other. Okay, so so this is just an illustration that with these optimal transport methods, you can actually say something about these discrete systems, about these quantum systems, in particular related to concepts like entropy, Fisher information, and rates of convergence to equilibrium for Markov chains or for these quantum Markov semigroups. Okay, yeah, I think I'm sort of kind of reaching the end of my time, so maybe this is a good place to stop, and thank you for the attention. Thanks.
Thank you, Jan, for the very nice talk. Is there other questions? So briefly.
Yes, so this question may be related to the question of Philippe. So is there a relation, what will serve as your Brownian motion? Is it related to the semicircular law? So the semicircular law will have a compact support. And your Brownian motion probably will have non-compact support. So are they related by the arc tangent or something like that? Or there is no relation?
Yeah, okay, so I mean, you're right, of course, that okay, so another important setting in this non-commutative probability is the setting of free probability, which sort of arises as a limiting case of random matrix theory. Also, optimal transport has been analyzed and has been kind of fruitful in this setting, and actually many of these inequalities have also been obtained in this context. But somehow the setup is a bit different, and I don't know how to directly relate sort of this kind of dynamical point of view on density matrices to the optimal transport in free probability. So yeah, my understanding is that these are two sort of different non-commutative generalizations of a classical object, but they're not directly related to each other as far as I know.
Can you hear me? Can you hear me, Jan? Yeah, so I have two questions actually. So the first one is, if I look at your lower bound on Ricci curvature for discrete spaces, do you have some consistency guarantees? For example, if I take a smooth compact manifold, I endow it with the uniform measure, and then I just draw points uniformly at random from it, and I form some sort of a nearest neighbor graph. Is there some notion according to which the nearest neighbor graph is going to be to have its Ricci curvature, which is lower bounded by something that tends to the Ricci curvature lower bound for the original manifold, for example? Like, are there some results like this that for example, the Lott-Sturm-Villani, a lot of the work is to check that this thing is consistent with the manifold setting. Is there something like this for your, like having some continuous objects for which you can define the Ricci curvature as limits of graphs?
Yeah, that's a good question, of course, to ask for some consistency. So I think that the particular thing you're asking is maybe too much to hope for. So if you put sort of points in a random fashion, then you're very quickly going to destroy some bounds on the curvature. So if you want to preserve this curvature at the discrete setting, you would actually need to have some rather kind of well-structured kind of symmetric settings. But sort of the passing to the limit in this optimal transport problems, that's also something that has been studied quite actively. So, for instance, in the setting of these random point clouds, there's nice work by Nicolas Garcia Trios, who I believe is actually, I'm not sure whether he's in Berkeley. I thought I saw him on the video, but I was not.
Yeah, he's
sure.
Here. He's in the room.
Oh, he's even there. Okay, yeah. So he has some very nice results on convergence of this dynamical optimal transport metrics to Wasserstein metrics in the continuum for random point clouds. So there are some good convergence results in this respect. But sort of if you start with a continuous object and you sort of you discretize with sort of random points, then I think you will not preserve the curvature. So if you start with discrete objects with good curvature bounds, then the curvature should be preserved at the limiting level. I think that's the direction in which things should be better.
So my second question is, so when you listed, all the pros of having this, Wasserstein gradient flow interpretation of JKO, you mentioned discretization in time, but somehow I feel that, the one that I personally found the most interesting is discretization in space and having this like deterministic particle evolution interpretation of it, where you just push everything according to optimal transport maps rather than like diffusing along some random diffusion that's like moving you all over the place. And, this is what, motivates all this SVGD type of approaches. One thing that I did not see from your formulation is, do you actually get deterministic velocities out of when you solve your problem? So you have this, so you say, I want to get an equivalent of JKO for discrete spaces. There's two objects. One is the entropy and the other one is the Wasserstein metric. And rather than, you could have said, I want to keep the Wasserstein metric and I want to change the functional, but you decided to keep the functional and change the Wasserstein metric. Is this Wasserstein metric giving you velocities when you actually solve this? Like when you look at the gradient flow, would this tell me how to deterministically evolve a particle so that it's going to converge to some distribution, a system of particles, so that it's going to have approximately limiting distribution pi?
Yeah. So okay. So I think you asked a few things, right? So it's true that I chose to keep the entropy and sort of I changed the metric, right? So if I would I mean, it depends on how you would phrase the question, right? But if you would want to stick with a Wasserstein 2 metric also in the discrete setup, then there's no hope to get a gradient flow.
Okay.
Because you don't have any curves of finite length. So I think you have to do something kind of this dynamical, in the spirit of this dynamical optimal transport. So then, the other thing that you asked, okay, so do you get, so do you get velocities for particles? That's the other thing you asked, right?
That's right.
Yeah, so not really, I would say. Okay, because so this discretization gives you kind of evolutions of probability densities, but it doesn't give you it doesn't say something about kind of the motion of individual particles. And actually, these things might be a bit counterintuitive also, because so for instance, suppose that you want to look at this discrete dynamical transport metric, like on a say you do it on a triangle, right? So a very simple discrete space, just 3 points, and you have some mass at one vertex, or a Dirac at one vertex, and you want to transport it to a Dirac at another vertex. Then actually, what will happen is that some of the mass will actually go through the third vertex, and so not all the mass will go through the shortest path, but actually some of the mass will go through the third vertex. That turns out to be cheaper than doing everything on the sort of the naive path, what you would think. So the optimal transport actually might it might split. So it gives you kind of sometimes a bit counterintuitive results, and I don't think you get. I mean, I don't think you can. It tells you something about motion of individual particles.
Lecture, do you want to comment?
I'd like just to comment a little bit on that. Overall I agree, but there is a little bit of something that saves you. So namely, what he wrote, when you wrote down the Benham-Grenier formulation, you basically are getting a non-local transportation of graphs, right? So you have these potential psi I and psi j, and they are really telling you how is the mass being transferred on a graph. So if the particles are not moving in this Lagrangian setting that they're moving, but you know exactly where is the mass moving. So mass can move along any or along any edge, as long as actually, in this case, psi j would be greater than psi I. So when you have the gradient flow, you will still have your potential, which is given by the logarithm of the of mu, right? And you will be transporting along those paths. So your particles can split. You can actually be approximated by a Markov chain, and this for some simpler equations has been done by Erbar, Vlachos, Schlichting, and Fatih, right? In that paper, so there actually exists a genuine particle approximation of this, but again, instead of the local transport, you have the no-local transport that can split particles, but you can still track where did the mass go. And for a heat, it goes approximately up down the non-local gradient of the logarithm.
But there's no unique choice for the path that you have. It's just telling you at time t, I have this potentials on my vertices. At time t plus dt, I have those, and I can really do whatever I want. Like if my particles have numbers, I can really just shuffle them any way I want. So I actually get this potential next time.
I don't understand what you mean shuffle. You still know where the mass is and how it is being transported. Then in the limit.
I thought you were telling me I just know how much mass I should have at a particular vertex at time t, how much mass I want at this vertex or at any other vertex at time t plus dt, and then how I move the particles to get from t to t plus dt is really up to me.
No. You actually have potentials and edges along which you transport. So you exactly transport along the edges as using the continuity, the non-local continuity equation on graphs that Jan wrote when he wrote out his Benham-Grenier description. So it's actually deterministic. The motion, how the particles go, right? There is a deterministic dynamics even for the heat equation.
Okay, so that's what I was asking. Okay,
right.
Okay, so
yeah, that's right. So you have exactly that. So the only thing that you don't have, in the continuous setting, you would write an ordinary differential equation for your particles, where the velocity is given by these velocity vector fields, right? In the discrete setup, I don't think you can write an ordinary differential equation for this discrete velocity vector field.
Okay, so another question?
Yeah, so in the last slide, you showed an LSI kind of an inequality for the example that you showed with the non-commutative semi-group. Does that imply also some sort of a commutative measure? And more generally, this technology that you're presenting, would that be extended to develop concentration equals or concentration measure phenomenon for non-commutative spaces?
Yes. Yeah. So okay. So I showed this kind of logarithmic Sobolev type inequality.
Yes.
Yes. So okay. So you can actually go further, and this logarithmic Sobolev inequality it implies some version of Talleyrand inequality, which actually bounds this Wasserstein distance in terms of the entropy. And you can use this inequality to also formulate some non-commutative analog of concentration inequality. So there has been also work by Data and Jose in this direction. So it is possible to turn this into some concentration statements in this non-commutative setup. Yes.
Yes.
Yeah, is it possible to relate this dynamical transport distance on graphs to the dysfunctional standard W2 distance up to some error term, which depends on the discrete nature of the problem?
So to relate it to a discrete W2.
Yeah, exactly.
On the graph.
So the one that didn't work for
yeah. Okay. So the results that I know. Okay. So what you can do is you can actually, because if you do this on a graph, then you can actually obtain two-sided bounds for this dynamical transport metric. So you can actually bound from below by the Wasserstein 1 metric, where you actually take Wasserstein 1 with respect to the graph distance. And you can bound this dynamical metric from above in terms of W2, where actually you build your W2 using kind of a distance between a distance on the graph, which you get by sort of restricting your dynamical transport metric to Dirac's. And so you can sort of bound it from below by W1. You can bound from above by W2. I think it should be possible to get error bounds there as well, but I cannot directly point you to any references on this. I'm not sure whether anybody computed this.
Okay, thank you.
So Jan, you mentioned in the beginning, like in the classical setting, large deviations. Do you know like any analog equivalent in the quantum case?
That's also a natural question. No, I think this is not understood. How these metrics relate to large deviations in the quantum set. No, I don't think that there's any understanding there.
So let's see, is there any other question? So Jan, thank you very much for staying until late with us. Thank you for the very nice talk. So I would thank Jan and all the speakers of the day again.
Oh, very nice. Like that.
Yeah.
We can fix this graph W2 extensive conversion.
Yeah. The finite discretization level, I was expecting.
Just for a second, oh my gosh, I saw that you don't hold.
Two minus
I don't know, it must have been
constants, which
exactly in my field.